Good afternoon, ladies and gentlemen, boys and girls, or good evening. We are going to be talking about Chapter 5 today, and basically what Chapter 5 has going on is it's going to be talking about heat and how heat is transferred and things like that. So again, we're in Chapter 5. And we're going to be talking about the first law of thermodynamics very quickly. We're going to get into some exothermic versus endothermic things like that. So let's just define. First law of thermodynamics is defined down here as energy is conserved. Energy lost by a system must be gained by the surroundings and vice versa. And really what we mean by that is, let's imagine we have a beaker. We're going to use this kind of illustration quite a lot. And we've mixed some chemicals into this beaker. And what's going to happen is we have energy flowing out, maybe in the form of heat. Now, what we would be focusing our attention on is the chemicals in the beaker, and that's what we define in chemistry as the system. Everything else around that would be the surroundings, and that would be the air, or the table that the beaker's sitting on, or even your hand that was holding the beaker, and we would define those as our surroundings. And so we're going to kind of refer back to systems versus surroundings a lot in this chapter. Now, coming down here, if we're going to be talking about endothermic reactions or endothermic processes, these are going to be processes where energy is going to flow into a system. So again, let's take this idea of a beaker, and maybe we have some water in here, and into this beaker we're going to put something, a chemical. Let's say we're going to put some ammonium nitrate in here in a solid form, and we're going to dissolve it. Now what's going to happen is this solution is going to start absorbing energy, once again in the form of heat, from its surroundings. It's going to absorb heat. We'll say it over here. Heat will flow in, which really is what that endo part of the thermic means. In thermic referring to temperature or heat. So heat is going to flow in. If we were to hold this in our hand, it would feel cold. Now the reason why it feels cold is because of the way heat flows, and we'll talk about that here in a little bit. But if we were holding this in our hand, I'm going to draw a little hand here. And there's a hand. The hand is going to be, we'll say 98.6 degrees Fahrenheit. And let's say this temperature over here is dropped down to like 40 degrees Fahrenheit. So what's going to happen is our heat is going to flow from our hand into the cooler solution, and that's why it feels cold. But really where the endothermic flow is because we're having an absorption of heat. Okay, now coming down here, we can also talk about an exothermic reaction. Exo meaning out, and so this is going to be energy that's going to flow out of a system. And so, again, we can use the idea of a beaker here, and let's say in this case we take some sodium hydroxide solid and we place it into the beaker. What's going to happen here is heat is going to flow out, or energy is going to flow out. What we're going to call an exothermic reaction, with this heat flowing out of the system. And again, if we take our hand, once again 98.6 normal body temperature. This temperature might be, I don't know, let's call it 120 degrees Fahrenheit, depending on the amount of sodium hydroxide we place in there. So the heat is going to flow in this direction from the beaker into our hand holding the beaker, which would be the surroundings or the air or the whatever we're placing this guy on. It's going to come up down here a little bit. Now let's talk about heat transfer and you might be getting the idea now that heat is going to be transferred. Heat itself is going to be an energy. We use the Q symbol for heat, and we're going to change that as well. It's going to be transferred from a warmer object to a cooler object, which hopefully you saw in the previous examples. But if we'll give you another little example. Let's say we have a block of, let's say it's pure copper, and it's 100-gram block, and this copper was heated up to 100 degrees Celsius. It placed in boiling water, 100 degrees Celsius. Let's say there's another copper block. We place it right next to it. same exact type block, 100 grams, but this guy's going to be 0 degrees Celsius. We just got out of a freezer. Now, so we have two different temperature blocks placed next to each other, and we're going to have some heat flow occurring. So heat is going to flow from the warmer object, which is the 100 degrees Celsius block, to the cooler object. So heat is going to flow generally in this direction, warming up the 0 degrees Celsius block, cooling down, and we would expect after a certain amount of time we would end up at about 50 degrees Celsius, and then it would continue losing heat to the environment depending on what the external environment is all about. Now, being more specific, we talked about heat up here as Q, and well, we're going to use another word for it, and this is called enthalpy. Now, enthalpy is going to be, we're going to use delta H. That triangle means delta, which just means change. And so we're going to call this heat gained or lost is our change. And it's going to be at a constant pressure. So essentially enthalpy is just the same thing as heat, but it's at a constant pressure. Now we do use enthalpy very often when we're talking about exothermic and endothermic reactions and the signs that are associated with these. So that's really important. So in an exothermic reaction down here, if we are talking about enthalpy or heat at constant pressure, the sign of delta H is always going to be negative for an exothermic reaction, basically because heat is leaving the reaction or it's being given off to the environment. Where in an endothermic reaction, delta H is going to be a positive value because heat is being gained. Heat's going in. And so let me give you some examples of what we're talking about. The example of delta H value. So here we go. Let's say we have an ice cube melting. Now, if we have an ice cube, which is, obviously H2O in its solid form, in order to get it to melt into, maybe a puddle of water, we have to add heat. And if we add heat and our focus is the ice cube, oops, sorry about that. We're adding heat again and our focus is the ice cube. What that means is heat is going in. This is endothermic, and so our delta H value is going to be positive, whatever positive value that actually is. Looking at this next one here, we have a gram of butane combusting with oxygen to give off carbon dioxide and water. Now, usually combustion reactions are going to be reactions to give off heat, and butane is basically lighter fluid, so it's what you're going to find in a little Bic lighter. And we know that's going to get hot. It's going to give off heat. So if the lighter or the flame is our, so I don't know, draw a little lighter here, and there's that wheel on it, and there's a flame or so. That doesn't really look like a lighter. But it's giving off heat, right? So this is going to be exothermic. And anything that exothermic is going to have a delta H value that is negative. Make that a negative. Okay, water freezing. So if we have, a puddle of water, or we have some water, and we want to turn it into a solid form, make it an ice cube, put it in an ice tray or something like that. So this is going to be liquid. This is going to be a solid. We're going to have to remove the heat to get it to freeze, and so delta H is going to be removing the heat, exothermic, which is negative. And a lot of students think, well, how can making ice, which is colder, be exothermic? But we have to remove the heat, and that's the definition of really what's going on there. Water boiling, we're going from a liquid to a gaseous form, and we have to, the only way to get it there is to add heat. I lie when I say that's the only way to get it there, because there is other ways to get it there. Pressure changes do it as well. But we're going to add heat in most cases if we're at standard conditions. So adding heat is endo delta H is going to be positive. Last one is water condensing, which is the complete opposite of water boiling. So going from a gas to a liquid because we are removing heat. And delta H, again, is going to be negative. It's exothermic reaction. Now, the next thing I want to talk about real quickly here is we can have what we call thermochemical equations. And these are chemical equations that are going to show the enthalpy change. So let me give you an example of an exothermic example. We can write them two ways. Let's say we have methane burning an oxygen to give you carbon dioxide plus water. One of the ways we can show an exothermic example is we can actually put the heat value over here, and if I put it over here, this is going to be an exothermic reaction. Now, if I don't put the heat value over here and I just put it separately, I might put down here delta H is equal to negative 890 kilojoules per mole. That would let me know also that that negative sign is exothermic. But if I put it on the product side, it also tells me it's being given off, and that helps the reaction occur. Endothermic example would be any example that the heat was on the reactant side. So if we had heat, the word heat, or even some values plus, let's say, a couple products, and you're going to A, B like that. This would be an example because the heat value is over here on the reactant side. This is going to be an endothermic reaction. We could also write delta H as a positive value. That would let us know as well.